we're going to study about the quantum mechanical model of the atom. Let us look first with the Bohr's model of the atom. Bohr's atomic model describes the atom like a solar system, where he considered electrons as particles moving around the nucleus in specific circular paths called orbits, much like the planets following its orbit around the Sun. These orbits are found at fixed distances from the nucleus. Much later, scientists discovered that it is impossible to determine the exact location of electrons in an atom. So, Bohr's idea that electrons are found in definite orbits around the nucleus was rejected. Three physicists led the development of a better model of the atom. These were Louis de Broglie, Erwin Schrödinger, and Werner Heisenberg. De Broglie proposed that the electron, which is thought of as a particle, could also be thought of as a wave. Schrödinger used this idea of de Broglie that electrons are wave particles to develop a mathematical equation to describe the probable location of an electron around the nucleus. On the other hand, Heisenberg discovered that for a very small particle like the electron, its location cannot be exactly known, which he called the uncertainty principle. These scientists believe that there is only a probability that electrons can be found in a three-dimensional space around the nucleus called atomic orbitals. De Broglie, Schrödinger, and Heisenberg arrived with the idea that the quantum mechanical model of the atom describes the probable location of electrons within the atom using atomic orbitals. As you can see in the animation, there are different kinds of atomic orbitals that differ in the amount of energy and shapes where the electron probably is. The quantum mechanical model describes the region of space around the nucleus as consisting of shells. These shells are also called principal energy levels. Electrons closer to the nucleus are at a lower energy level and have lower energy than those farther away from the nucleus. When you look at the periodic table of elements, the energy levels of the atoms corresponds to the rows of the table. For example, period 1 corresponds to first energy level, while period 5 corresponds to fifth energy level, and so on. The principal energy levels are broken down into sub-levels. These sub-levels define the orbital shape. Spherical shape for s orbital, dumbbell for p orbital, cloverleaf for d orbital, and complex for f orbital. The principal energy levels are always equal to the number of sublevels. For example, the third energy levels have 3 sublevels, s, p, and d orbitals. Each sublevel has different number of orbitals. This is due to the orientation of the sublevels along the x, y, and z axis. Thus, there are different orientations in space for p, d, and f orbitals, except for s orbitals because of its spherical shape. Each orbital can hold a maximum of 2 electrons. Since the p, d, and f orbitals have different number of orientations, each orbital orientation also holds a maximum of 2 electrons. Thus, the maximum number of electrons that can occupy a principal energy level is given by the formula 2n squared, where n is the principal energy level. Therefore, the quantum mechanical model describes the probable location of electrons in atoms using its principal energy levels, sublevels, and orientation of orbitals in a three-dimensional space.